Hi, this is Roger from Labs, and this will be the first part of an explanation of our spreadsheet for calculating magnetic antennas, especially resonant magnetic antennas. So we will go through each entry step by step, but first of all a few words as an introduction. First of all, you get this as an open document template file. You can open it with OpenOffice, LibreOffice and the Microsoft Office package. I've chosen a template so that the formulas that are behind some of the cells, that you cannot by accident delete them or change them. So if you want to store your results, just store it as save as, give it a new name, and the original template will always keep intact. So next is, you can see here as a little hint, the yellow values are those where you have to input something, and the green values are the calculated values. And you can see there are also some intermediate calculations which are in white. We will explain each cell step by step. Now, because most magnetic antennas are used in conjunction with a tuning capacitor to give a resonant tank circuit, the first part here is just to calculate when you have either your frequency and your tuning capacitor capacitance given, or two of the other variables, to calculate the necessary inductance. And we will just start with the simplest of all examples, and that is a single turn loop antenna. The units here, you don't have to input the units. They are also in the formatting. So if we start with our desired tuning frequency, let's say we want to tune our antenna to 10 megahertz, or in other words 10,000 kilohertz. You only input the 10,000, nothing else, and by magic the kilohertz appears here as a formatting sign. Another hint, you can see that this is the European convention how to use the decimal point and the comma. That is a little bit just reversed to the way you use it in the US. So you can change the settings of LibreOffice or OpenOffice just to make it the way you want it to. So we have our 10 megahertz tuning frequency. Next is, in this higher frequency range, we usually use tuning capacitors with relatively low capacitance values. So let's say we're using a 50 picofarad capacitor, and again only input the 50, not the PF or picofarad. And the first calculated value is that we need an inductance of 5.1 microhenries just to tune with a 50 picofarad capacitor to 10,000 kilohertz or 10 megahertz. If you have the other values, if you have a given inductance and a given frequency and want to know which tuning capacitor you need, you have the second formula here, and the third formula for given inductance and given capacitance, just to calculate which frequency does this combination of inductance and capacitance tune to. You get the result here. And as you can see in the original, in the template, if you input here on the left side, which is the most used input values, if you input them here, the values are automatically copied to the right side. But you have to remember that for further calculations, only this cell here is used, not the other ones. So if you make a calculation here with the other ones, you have to manually transfer or copy the value here to this cell, because this is the starting point of all calculations. So the next thing you have to input is μr, the relative permeability of the material that you wind your coil onto. Now, if we have a loop antenna where we don't use any ferrite materials or anything else, then as you can see as a hint, you input simply 1. 1 is for air or vacuum, and so that is the default value. So next is the most important value we want to know for a loop antenna is which diameter do we have. And now we have to, this spreadsheet is not universal, so you sometimes have to do a little iterations. What we want is, we want exactly 1 turn, because we start with the example of a 1 turn or single turn loop antenna. Now we just have to fiddle around a little bit just to get exactly 1.00 turns. You can see here in bold numbers, this is rounded, but we need exactly 1.0 turns. So we just enlarge the diameter. Here it is stated as winding diameter. That is simply because later when we calculate ferrite antennas and etc., then this is of course the diameter of the winding. A single turn loop antenna of course has, well, not a kind of winding, it's just a single turn. Now let's enlarge this and play a little around a bit. Let's enlarge this to 1000 millimeter. We still are a little bit nearer, 1.43 turns. Now let's go to, becomes quite large, 1.5 meters already. We're quite near 1.15 turns, so let's see what 1700 millimeter gives. We're still nearer, and 1800, so we're nearly there. So this will be exactly enough. So we need quite a large winding diameter of, or simply diameter of our single turn loop antenna. And the next, there's one thing I forgot. Usually loop antennas are round, and here you have a field where you can select between square and circular, and of course we go back to circular, so the default value was square, and we're still a little bit too high, so we still have to enlarge the diameter. 2100, still not enough. 2200, also not enough. 2400, so that is the result for the diameter of our single turn loop antenna. So we're with 1% accuracy, that is near enough. So that is the first result. When we want to tune to 10 megahertz with a 50 picofarad capacitor, here also including parasitics, just remember that a normal variable capacitor, you always have some parasitic capacitance through the cables and wiring, etc. So you have to just add a little bit of capacitance to the nominal value of your tuning capacitor. So anyway, first result is we need 2.4 meters of diameter if we have a circular, which is the usual shape of a loop antenna. If you use a circular shape, if we would use a square shape, of course, we have to correct the value. As we already have seen, it's then quite small, a little bit smaller. So what's next? Now we want, and that is one of the most important things, we want to calculate the Q factor. And I've done an extensive video series about what everything affects the Q factor. Now, the first idea that comes to mind, just to counteract the skin effect, which will be the first effect that we have to deal with, is, well, we're using litz-wire, as you know from old AM radios, the ferrite rod or loopstick antenna there, which was wound on or not on with litz-wires. So we take just a guess. Let's say we use 90 single strands of litz-wires and each with 0.1 millimeter. Well, that's perhaps a little bit too large. Let's take 0.03 millimeter skin diameter. Here you have some additional information about the effective cross-sectional area of your litz-wire. In this case, when we have 90 strands, each 0.03 millimeters in diameter, we get 0.06 square millimeters. But this, as you see, there's a little error, determines only the DC resistance, because as we can see a few cells below, the skin effect comes into play. Now we have to choose the material that our antenna or our loop is constructed of. The default value is copper, and you can see you can manually input other values. Copper has 0.017 ohms times square millimeter divided by meter. You could also input silver. As you can see, silver is only a few percent better than copper, and I've also made another video that I'm quite against using any kind of silver-clad wire, no matter if it's silver-clad copper wire or anything else. In special cases, even aluminium, brass, steel, gold, etc. So there's a list of quite a few used materials, but of course our standard material in electronics and in high frequency use is, first of all, let's start with copper. Now we get an additional value. The specific DC resistance of this copper litz-wire is 267.2 milliohms per meter of length. And now we get the DC resistance. That is already quite high. It's 2 ohms. We will see just in a minute how this affects skin effect, or how the skin effect affects the DC and the AC resistance. Now the next calculated value is the skin depth. So at 10 megahertz, the wave or the current only goes 21 micrometers into our wire. So even if we use a litz-wire with 0.03 millimeter, then the skin depth, as you can see, 21 micrometer is the same as 0.021 millimeter. So this is quite fitting. The high frequency current just uses nearly all of our litz-wire, so that is quite okay. Here are again some intermediate calculations. And now we get the skin resistance of 2.2 ohms. As you can see in brackets, already includes the DC resistance. So we have the pure copper resistance just for DC current is 2.015 ohms. If we include the skin effect, this is raised for just a few percent to 2.20 ohms or 2.20 ohms. And the skin factor, that is the ratio between the pure DC resistance and the DC resistance including the skin effect is just 1.09, which means we only have a 9% added resistance due to the skin effect. So at first glance we can be quite content with our skin resistance here, which or with the choice of using this litz-wire here, because the skin effect does not perceptibly increase our DC resistance at 10 megahertz. All these factors here are frequency dependent, so everything I'm saying is valid from this point on here, or from this point on here, is valid only for 10 megahertz. For other frequencies you get other values. So we can be quite content with this 2.2 ohms. We have counteracted the skin effect by using litz-wire, but what is mostly forgotten or neglected is the so-called proximity effect. And we have the proximity effect. I've explained this in another video, in the video series about resonant magnetic antennas. So anyway, proximity comes into effect when we have neighboring wires that carry the same current or the same frequencies. Now you would say, well, we have a single turn antenna, so a proximity effect cannot come into play. Yes, you are right on the one side, but we have chosen litz-wire. And of course, then we still have the internal proximity effect between the single strands of the litz-wire. So you can see here, between each turn, the external proximity effect, that does not come into play. We have only a single turn, so there is no the resistance, the calculated resistance, is the same as only for skin effect. But here we have the internal proximity resistance between the single strands of our litz-wire. And you can see here experimental. This is not 100% correct. It only gives you a rough idea, because this is, you can hardly find any formulas for this. So here you can see that the internal proximity effect between each single strand of our litz-wire, that raises our total resistance by a factor of 6. And now we get a Q factor of only 24. And that is of course much too low. We get a incredibly large bandwidth of 440 kilohertz. So our first result is using litz-wire for a loop antenna in the higher frequency range. Anything above 1 megahertz, that is the limit up to which you can use litz-wire to advantage, ruins our Q factor. The DC resistance was okay at first sight. The counteracting of the skin effect with litz-wire was also okay, but litz-wire has the disadvantage that there is the internal proximity effect, and this totally ruins our Q factor. So this antenna would be unusable, or would be of extremely low quality if you try to build it out of litz-wire. So next idea is, okay, get away with litz-wire. We change to a single thick copper wire with, let's say, 1.5 millimeter. Let's see if this gets better. Now our DC resistance has dropped drastically, but in radio frequency DC resistance is of no importance. Important is first of all what is about the skin effect. And now we get a skin resistance of 2.64 ohms. That is a little bit higher than we had with our litz-wire. But now we don't have any more external or internal proximity effect. You can see, taking into account the external proximity effect has no effect because we only have a single turn, and the internal proximity effect also doesn't come into play, simply because we only have a single thick copper wire and no longer litz-wire. So what Q factor do we get now? We get, of course, then the total series resistance, taking all effects into account, is 2.64 ohms. And we already get a much better Q factor of 121. So you might, if you ever have seen diagrams or data sheets where Q factor is specified, you would say, well, one Q factor of 121, that's quite okay. It's not so easy to get much higher than 120, but with 10 megahertz, we still have a bandwidth of 80, rounded up 83 kilohertz. That is still much too high, because remember, ham radio stations are separated by only 5 kilohertz. So if you have two ham radio stations by chance on a neighboring channel, and they both come with the same signal strength, then you would hear both of them if you're only using the one-turn loop antenna with this Q factor. So now let's think what we can do to get a higher Q factor. Well, we can of course raise the diameter, but of 1.5 millimeter, I think, is the maximum of wire that you can really bend easily, etc. But we now could change to copper tubing, because we know, due to the skin effect, anyway the current is flowing only on the outer sheet of a very thin layer of 21 micrometer. So we don't have to waste all the copper inside a solid copper wire. We just use copper tubing, because anyway we only need the outer 21 micrometer. And of course you don't get copper tubing with such a thin thickness. But anyway, copper tubing is much cheaper, easier to get for installation work. You can buy them at home improvement stores, etc., or eBay or wherever. So we make a big jump. We go to 20 millimeter copper tubing. Let's see. So the DC resistance now drops to below 1 milliohms. So I only have 3 decimal places behind the comma. So better to take 4 decimal places. Anyway, the skin resistance now has dropped again drastically to 0.2 ohms. And now, that's what we want to see, a Q factor of 1618 and a bandwidth of 6.2 kilohertz. So that is really what we want to reach. And the only way we could get there was to get to such a high Q factor is, and correspondingly, a very narrow bandwidth of only 6 kilohertz. So we could really separate 2 neighboring stations, even if they are at neighboring channels, and have nearly the same amplitude. So that's where we want to go. But now in practice, in the real world, you have to remember, well, every contact resistance has to be below 0.2 ohms. So we have to take every precaution to ensure that we have nowhere any resistance higher than, let's say, 10 or 20 milliohms, for not to ruin the Q factor again by contact resistances. because you can see here, this is the total series resistance, and if you have any contact resistance additional or in series to your loop made out of thick copper tubing, then this again would lower your Q factor. But let's sum up the result. At a moderately high frequency of 10 megahertz, which is not the upper end of the ham radio frequency bands, it's just in the middle. Yeah, but even for 10 megahertz, we cannot use litz-wire because of the internal proximity effect. We cannot use solid copper wire because the practical limit is somewhere between 1 and 2, let's say even 3 millimeters would give a much too low Q factor. We have to go to very large diameters. In this case, just for an example, we choose 20 millimeters, which is still very well handleable or manageable. And well, then we get a Q factor in the range above 1000, and that's quite a nice result. So let's sum it up again. For high frequencies, do not use litz-wire. It's absolutely useless. Do not use thick, solid copper wire because the necessary diameter would be much too large to handle it. The only way we can get away with is using either copper tubing. We could even use copper foil and bend it to a toroidal shape and use this. But anyway, you have to go to very large diameters to counteract the skin effect and to get to a below 1 ohm total series resistance, and in consequence to get a correspondingly high Q factor. So this was the first example. Just in the meantime, until the next episode, you can play around. Perhaps you find still some errors in the formulas, etc. Anyway, I hope you liked it, and have fun with playing with the freely downloadable spreadsheet, and see you next time. Bye from Roger. Bye from Kanka Labs.